All right. Hello, everyone. There has been a sort of last-minute schedule change. So if you looked at the schedule yesterday, you would have seen that it was supposed to be Jutta Steiner here talking about parity, but instead you have me. So if you expected Jutta, I'm sorry to disappoint. I couldn't possibly fill her shoes. But instead you get me talking about running Rust contracts on Kovan with WASM. And that's also the reason why I wasn't lumped together with the WASM talks yesterday. So if you watched them yesterday, then you have a little bit more today. My name is Fredrik. I'm a core developer at Parity Technologies. That means I mostly work on the Ethereum client, but I also do some other stuff, and I spend a lot of my time thinking about how to make blockchain development better, both for infrastructure developers and app developers. At Parity, we have these roughly 3 areas that we operate within. One is partnerships with companies and organizations that rely on our software. We help large and small companies alike through enterprise projects and advisory. We do what we call core infrastructure development, and that's what I'll be talking about here today. And finally, we're contracted by the Web3 Foundation to build the first implementation of Polkadot. So core infrastructure, what does that mean? It's mainly an Ethereum client that you can use to run mainnet, but you can also use it to run a local development network or on testnets or spawn up your own networks. But really, it's Ethereum plus a bunch of other things. So we have a thing called Secret Store that's a distributed key generation mechanism that allows essentially contracts to store and distribute secrets. We have private transactions that allow a set of nodes to privately transact and commit an encrypted state to chain. Our Parity client features a pluggable consensus module so that you can replace proof of work with proof of authority or proof of stake or anything else that you might want for your chain. And we recently shipped, or actually, all of these are kind of recent ships, but we have permissioning, which is sort of low-level configuration options that lets you set permissions on a network. And these are also controlled by smart contracts, so you can say that only this IP is allowed to connect to the network, or only these accounts are allowed to deploy contracts. We have a JavaScript library that we call the bonds library, which is sort of a high-level reactive declarative library where you just say what data you want from the blockchain, and it uses our pub/sub layer to automatically update that data when there's a new block. And finally, what I'll talk about here today is our WASM VM that we're shipping very soon. And we also have a bunch of other stuff going on, but these are sort of my own personal top picks of stuff I think is cool. So, WASM and WebAssembly. For those of you who missed the 5 talks yesterday, I'll do a very quick recap. It's a standard developed by a W3C work group that includes Google and Mozilla and a bunch of other people. And it has major browser support by now, and it's quite well adopted. It aims to be a sort of low-level assembly-like instruction set that can run in the browser. Because it runs in a browser, it has to be high performance. You don't know what this browser is running on. It may be some mobile device. And we also want a compact representation, so small binaries, because, again, we're shipping these things over the internet to devices that we don't know what connection they have. LLVM has target support for WASM, which is a pretty big thing. So there's a bunch of languages that uses LLVM as its backend for compilers, which means that you get like 15 years of compiler optimization for free if you use WASM. Why WASM for blockchain? So there's the core idea of sort of standing on the shoulder of giants. There's been many years of work put into WASM, both by compiler teams and by standardization teams, etc. We could probably get to the same stage with the EVM, but it would probably take a couple more years. But the main thing is really that it's very easy to make WASM fully deterministic. So if we compare to like the Java VM, the JVM has garbage collection and has a bunch of other things that make it non-deterministic, and it would be a very daunting task to make it deterministic. Whereas with WASM, you kind of get that for free as long as you exclude some operations. Basically means you don't have to change the VM really at all. You just pass your code through a validation layer. And of course, a boon of WASM as well is that it allows smart contracts that are written in any language. So TypeScript, C, C++, anything that goes through mscripting or LLVM or Haskell or Rust. Haskell probably a bit less suitable because it would have a huge runtime. And obviously we Parity are fans of Rust. We write Rust for basically everything we do. And we think Rust is a pretty suitable smart contract language. And that's what I'll kind of show off here today as well. So WASM on Kovan. For those of you that don't know, Kovan is a testnet. Its main goal is obviously that you should be able to deploy a contract, test it, make sure that it works, and then expect that it works the same on mainnet. But we also want a little bit more out of Kovan, so it's sort of a testnet plus. We like to think that we can sort of experiment with features there. We want to be able to ship secret store and let Kovan users experiment with having contracts store and distribute secrets. And WASM is another one of these examples where we want to try to ship this, see how it works, if people can break it or not, and if they use it or if it's useful. And it's currently targeted at block 6.5 million, which is very soon. What's important to note is that EVM and WASM will coexist on Kovan, so both will be there, both VMs will be there, and you'll be able to call an old EVM contract from WASM and vice versa. You can obviously also run all of this on a local development network today. That's what I'll be doing. And we've built some rudimentary tooling around this. So we have some libraries for Rust, and we have some tooling to make this process easy. So I'll try to attempt the most dangerous conference trick of all, which is a live demo. I briefly contemplated actually writing some code live, but I figured none of you actually want to see me sit here and write code, so I'll just walk through the code and then deploy it. So we start with this, which is an important feature of Rust, and many other languages have this feature as well. But it's something that's absolutely necessary if you want to build something for blockchain, and that is to be able to exclude the standard library that comes with your language. So by including this little statement, we get a completely blank slate, and we just get what we explicitly include. Then another very important feature to sort of consider here is that we can use whatever package management solution we have in our language already. So for Rust, that package management solution is Cargo and uses crates.io. So we've built a bunch of libraries like a library for hash types and a standard library for WASM contracts, a library for interacting with Ethereum, the externs, and some stuff to derive ABIs, etc. And we can just use our package management solution to automatically include these. We've published these on crates.io, and it's all sort of standard Rust. Then we get to the actual contract bit. So this is a donation contract. It's just like a simple hello world that I wrote up, and it doesn't actually do anything very useful. But you can see that we include an H256, which is a hash, a 256-bit hash. We have a concept of an address. And then from PWASM Ethereum, we include read, write, sender value, those kinds of things. Those are externs that pull in data from the sort of external environment of this transaction. So sender is whoever sent the transaction, value is how much ether they sent. Then, because all state storage in Ethereum is essentially a map of 32 bytes to 32 bytes. We don't really have a clean solution for doing state variables, but this is our solution for now, and we hope we can sort of fix this with some macros. And I think this is a good example of the stage we're in. We can sort of do stuff, but not everything is the way we want it to be. So we declared these three keys: total donated, top donor, and owner. And they're just like 1, 2, 3 in the first bytes, and then we store data in these places later. This bit, though, is sort of what's really clean and neat in the solution. We have a trait that fully defines the contract that we want. So it has all the types. You can declare whether it's a constant, whether it's an event, and the little thing on top of donation contract there shows that we automatically derive a JSON ABI from this trait. So we have our contract fully defined. Now we just need to write an implementation for it. This is what the implementation looked like. We declare a struct that is a donation contract instance. We implement the donation contract trait for this instance. And we have a constructor that gets called when the contract is deployed and only when it's deployed. The total donations reads from this key that we previously set and returns the value. And so you can also see in the constructor we're actually initializing this value to 0, and we're initializing the owner to the sender, essentially the deployer. We have a top donor that just returns the address of that donor. And the donate function reads the state of this from the sender and the value, and we can do whatever stuff we want there. And then finally, we trigger this donation event. We have a withdraw function that checks that the sender is the owner and they can withdraw. And we have this call that in this case is an ether transfer, but it could be a call to other contracts as well. And what's neat here as well is that after that last function, we actually fully defined our contract interface, but we can have whatever helper functions or libraries or whatever Rust code we want outside of this. So I put in 2 helper functions to call out an address from storage and to set the top donor if the amount is larger than the amount registered. Then we have this little bit of boilerplate that sort of makes all of this work. So the deploy function is what gets called when the contract is deployed, and only then. It dispatches whatever inputs to the constructor, and that's it. The call function is what gets called when you do any sort of calls into this contract. And again, we have a dispatcher that takes the inputs, runs it through the contract, and returns whatever value that function returned. So this is the sort of piping that you need to make your language work with Ethereum. And because we've learned from our mistakes, let's write some tests. So what's neat here again is that we can use the exact same testing infrastructure or whatever frameworks we want from our other projects and environments. So these are just plain standard Rust tests. We have the WASM test library that we import here, and that gives us a bunch of tools to be able to manipulate our external environment here. And if you look at this test, it just says that it should actually donate and tally up correctly. So we define 2 addresses. We use this ext update to update the external state, setting who the sender is, what the value is. Then we call the constructor. We check that it's initialized. We call the donate function, check that the total donations is actually 500. And then we can update the external state again, setting the sender to someone else, setting the value to something else. And then we call donate. It should tally up correctly to 750. The top donor should still be the first donor. And what's also neat is that we can get the log, so we can get values from this external environment as well. So we can check that there are indeed 2 log events. We could even check that they are what we expect them to be. So that's roughly what a contract in Rust would look like. Let's actually try to run our tests. And it compiles and ran the test, says it's okay. So I guess we're good to go. Now I can make this a little bit larger. Now we want to build, and so we build our release with the WASM 32 target. This is still just plain Rust, plain cargo. We haven't done anything special at all until this point. So we build it, it produces some WASM output, and then we do WASM build. So we have this little tool called WASM build. This is something that we've built, and this is where we get blockchain specific. So far, everything is just plain Rust. This takes the output, the WASM output from Rust, makes it into something that we can deploy on a blockchain. So we run that, and we get, I can show new. Here. This is the ABI that's output by compiling the Rust code. It's just a standard ABI. It looks like anything else that you would expect that you would get out of Solidity or anything else. And we can check a little deploy script here that I wrote. It just uses plain Web3.js, nothing special. We set the provider, which is the local host, set an account that has some gas in it, unlock the account, pull in the ABI that I just showed, pull in the data from the WASM binary, and deploy it. And hopefully this should work. So I have a parity node running here in one of my tabs. And we can just run deploy. And it's deployed. Because it's a local development network, it just instantly deploys and instantly gets mined. So we get an address for this contract. We can move over to the parity UI. Look at the contract, say we want to watch one, paste in that address, name it, and we need the ABI, so I'll just copy paste that, add contracts, and you can see we have a contract on our local chain. So it has these top donor and total donations functions. It shows an event list, which is empty, and let's donate some money into it. So here we see the two other functions, donate and withdraw. We'll donate 1,337. I feel very generous, and unlock, and it gets instantly mined again because I'm on the development network. Let's refresh the contract. It shows the top donors ETHCC, which is the account I was on, and total donations. We can flip the switch to show in ETH, and everything works as expected. We have our event, and what's important to note here is that this is just a completely plain standard parity UI. We haven't changed anything on the UI. All your dApps should work the same way, whether it's EVM or WASM VM, and it's really straightforward and nothing special here. So that's it for the demo. I want to say that this is ready for users to start playing and testing and making smart contracts in Rust or your own favorite language. We think this is super cool. We really like this, but we can't build everything ourselves here. We really want you guys to test this out, to tell us what sucks, to tell us what's great, and just join us. So all code is open source as usual. It's available on GitHub. We're available to mentor, guide, or just chat on Riot. We have a water cooler channel or a dedicated channel to WASM if you just want to follow that conversation. This is a list of repos that might be relevant. So parity WASM is the serialization and deserialization of WASM into Rust. We have the standard library for Rust contracts for Ethereum externs. And we have this repo WASM utils, which is like general WASM utilities. It's not really necessarily related to Rust. But if you really want to dig into this, I'd say start with the tutorial. It's a really great sort of step-by-step tutorial that walks through everything I just did here. And finally, I want to give a shout out to Nikolai, Sergey, and Alexei, who are the phenomenal Russian trios actually made this possible. Sergey is sitting right over here, so if you find him later, please buy him a beer. That's it for me, so thank you very much. So the question is if this is eWASM or if it's compatible with it. It's definitely compatible with it. So in one of the WASM talks yesterday, the guy said that eWASM is just WASM. They literally don't make any change to it at all. Neither do we. So eWASM is just WASM, and this is the same thing. There may be some differences in the sort of validation layer that we do, but if there are, they should be trivial to eliminate. And our goal is definitely to be compatible with everything else here. Why did we pick Rust? It's a good question. Rust stands at a very unique point of being type safe, safe against seg faults. It has no undefined behavior. It has no runtime, so it doesn't do garbage collection, doesn't do reference counting. You get very small, efficient code with it, and we just kind of like it. All right, if there's no further questions. There's? Oh, sorry. What's the performance comparison to EVM? Well, right now, we actually haven't benchmarked all that much. We know that we have some low-hanging fruit in terms of binary size. It produces binaries that are quite a lot larger than EVM right now. But theoretically, it should be much more efficient because we're not restricted to dealing with 256-bit integers. We have 64, 32 bits, and we can do a lot of other things. There are a lot of lower-level instructions. So theoretically, it should be much more efficient, but we haven't actually gotten to the point where we're optimizing and benchmarking comparing to EVM. What's the roadmap that we have in mind? So it's getting deployed on Kovan. We're hoping we can get a lot of good feedback from that, people actually testing this stuff out and using it. We have a sort of informal roadmap for writing Rust smart contracts specifically. We definitely want to not have to write all the bits in a hash to do storage. We actually want to do variables and have maps like you would have in Solidity. We also hope to maybe get down a line of being able to more clearly separate immutable and mutable code using the Rust type system. And then obviously it's just sort of performance optimizations, making things better on the WASM side. The question is if we're afraid of consensus failures due to differing implementations of WASM. We're not really at that stage yet where we're worrying much about that. I mean, we're deploying this to Kovan. If you manage to break it, we'll give you a couple $1,000 in a bug bounty. But the WASM standard is actually quite set. And because we're not actually modifying that standard in any way, we're just removing things from it. It should be relatively easy to agree on what operators do we exclude and just have a set list of that all VM implementations rely on. So it really should be quite easy to make sure that all implementations are fully deterministic and behave the same way. Can you deploy a custom private testnet? Yes, definitely. That's what I've done on my laptop here. It's in the tutorial. It shows you exactly how to do that as well. All right. Thank you very much for coming and listening.